After knowing the concept of reflection coefficient and transmission coefficient, now we are able to discuss a very important concept, which is actually Brewster's law and degree of polarization. To know the idea of Brewster's law and degree of polarization, we will start with Fresnel's equations, and these equations have already been discussed in previous lecture. So for convenience, I have just mentioned the Fresnel's equations or Fresnel formula, which you have earlier learned in the previous lectures. So see what are Fresnel's equations. In fact, you know, in two cases we define the Fresnel's equations. First case is actually when the electric field vector is parallel to the plane of incidence, and in second case we consider that the electric field vector is normal to the plane of incidence. And you know, when electric field vector is parallel to the plane of incidence, then actually the ratio of the amplitude of a reflected wave, which is E naught 1 prime, and the amplitude of the incident wave, which is E naught 1. This ratio is equal to tan theta I minus theta r divided by tan theta I plus theta r. And in similar manner, you can see I have written here the other three Fresnel's formula. Actually, the equation of interest in this discussion is this equation 1a. You know, this theta I is angle of incidence and theta r is angle of refraction. So now let us examine this equation 1a in a particular condition. In fact, in this condition, we consider that this angle theta I and theta r has such a value that their sum is equal to 90 degree. Let us consider it. So if we consider that theta I plus theta r is equal to pi by 2. In fact, in this condition, you can see from equation 1a, that is from the first Fresnel formula, you can see what will be actually the reflection coefficient. You can see this formula which is defined in this equation 1a. So then the reflection coefficient, which will be written as R parallel here, because we are considering the Fresnel formula in this condition. So how this R parallel is defined? You know, this is defined as E naught 1 prime over E naught 1 parallel. And in accordance with Fresnel formula, you know, this is equal to tan theta I minus theta r over tan theta I plus theta r. But here we have considered that this theta I plus theta r is equal to pi by 2. So you can see in this condition, this will be equal to tan theta I minus theta r over tan pi by 2. And you know, this tan pi by 2 is equal to infinity. So this will be equal to tan theta I minus theta r over infinity. And so this result will be equal to 0. So what you are seeing here, you can see that this reflection coefficient in this condition is actually equal to 0. This is a very significant result, that you can see that when theta I plus theta r is equal to 90 degree, then reflection coefficient R parallel is equal to 0. And so that you can say that when the reflected and refracted waves are perpendicular to each other, then there is no energy carried by the reflected ray. You can see here this is in fact an unpolarized unpolarized electromagnetic wave which is incident at an angle theta I on the boundary, and so the angle of reflection will be also theta I, and this is angle of refraction. So if theta I plus theta R is 90 degree, then what will be this angle? This angle is actually angle between the reflected wave and the transmitted or refracted wave. You can see, so angle between reflected and the refracted beams. If we assume that this angle is theta, you can see from the geometry of figure that this will be actually equal to pi minus theta I plus theta R. And since we have considered that theta I plus theta R is equal to pi by 2, so this will be pi minus pi by 2, and this is equal to pi by 2. So you can see that when theta I plus theta R is equal to pi by 2, in fact in that condition, this reflected beam of electromagnetic wave and the refracted beam of electromagnetic wave is actually perpendicular to one another. And so in this condition, as I have told you, that the reflected beam or reflected and refracted waves are perpendicular to each other, and there is no energy carried by the reflected ray. In fact, this angle of incidence for which theta I plus theta R is equal to pi by 2, or you can say that the angle of incidence which is actually equal to pi by 2 minus theta R, this angle is actually known as Brewster's angle or polarizing angle. Why it is called polarizing angle, we will see it later on. So you can see that this angle, which is actually called Brewster's angle. So in this condition, the angle of incidence theta I, which is actually equal to pi by 2 minus angle of refraction theta R, is known as Brewster's angle. Actually, Brewster is the name of the scientist. Brewster's angle, or it is also called polarizing angle. Why it is called polarizing angle? As I have told you, this will be clear to you as after some time. This is also called polarizing angle. Now, as this angle of incidence is called polarizing angle, so we denote it by a particular symbol theta p. So this polarizing angle is denoted by the symbol theta p, p for the word polarizing. Now we can find what will be the expression for this polarizing angle in terms of the refractive indices of the two media. And for this you can utilize the Snell's law. So you know from Snell's law that sine theta I over sine theta r, this equal to n2 over n1. You know this n1 is refractive index of the first medium and n2 is the refractive index of second medium. And so you can see when actually this angle of incidence theta I is equal to polarizing angle theta p, then this theta r will be equal to pi by 2 minus theta I, which is in this case theta p. So we can write this as sine theta p over sine pi by 2 minus theta p, and this will be equal to n2 over n1. Now you can see this is sine theta p over cos theta p, and this is equal to n2 over n1. So you can see from here this is actually tan theta p, this is tan theta p, and this equal to n2 over n1. And so you can see this polarizing angle or Brewster's angle is given as tan inverse n2 over n1. This is a most important result, and you know this particular angle theta p is known as Brewster's angle or polarizing angle. Now you can see this polarizing angle actually depends on the refractive index indices of the pair of the medium. Actually this equation 1, which is theta p equal to tan inverse n2 by n1, this equation is known as Brewster's law. So you can say this equation 1 is Brewster's law. Now you can see from this Brewster's law that if a plane wave of mixed polarization, or you can say if an unpolarized wave is incident on a plane interface at the Brewster's angle, then only the portion of wave with electric vector perpendicular to the plane of incidence will be reflected. In fact, the reflected radiation is completely plane polarized with polarization vector perpendicular to the plane of incidence, and hence the Brewster's angle is also known as polarizing angle. As I have told you, this is the reason why this Brewster's angle is called polarizing angle. You can see from here. So let us see first of all this figure here, which I have mentioned in this page, that you can see this is actually the symbol of unpolarized electromagnetic wave. The arrowhead and dot both are present, and this represents unpolarized electromagnetic wave. This unpolarized electromagnetic wave is incident on this plane boundary, and you can see that if this theta I, which is angle of incidence, if it is equal to polarizing angle theta p, then the reflected wave is completely plane polarized, and the plane of polarization, or you can say the polarizing vector, is perpendicular to this plane. So this has been shown by the symbol of dots here, and so this is completely plane polarized, and the polarization vector is perpendicular to the plane of incidence. At the same time, you can see that the refracted wave which exists in the second medium is also plane polarized, but in this refracted wave, actually the polarization vector is in the plane of the incidence. So this is a very remarkable fact regarding this Brewster's law, that you can see this conclusion here, that when theta I is equal to theta p and an unpolarized electromagnetic wave is incident on the boundary, then what will happen? The first important fact is that the reflected wave and the refracted wave are perpendicular to one another. This is one of the remarkable facts. One another. The another remarkable fact is what? The another fact is reflected wave is completely sorry, this is in fact wave is completely plane-polarized with polarization vector perpendicular to the plane of incidence. The another remarkable fact is the refracted wave is also completely plane polarized, but in this case polarization vector is in the plane of incidence. A refracted wave is also plane polarized, but polarization vector is in the plane of incidence. So this is another remarkable fact. Actually, there is also an important fact that in this case, actually the reflected and refracted waves are perpendicular to one another, and no energy is carried by reflected wave. So this is another important fact. Now let us take a particular example. You can see this figure, that if we consider that this second medium N2 having refractive index N2 is actually a medium of glass, and the first medium is that of air. So if we consider this particular example, that a wave enters into the glass from air, then what will be actually the polarizing angle? You can see what will be the value of this. We take a particular example. So if we consider that N1 is equal to 1, and you know this is refractive index of air, and we also take N2 equal to 1.5, and this is for glass. So in this case, theta P will be what? You can see this will be tan inverse 1.5 over 1. This is simply tan inverse 1.5, and tan inverse 1.5, you can see the standard table that this is actually 56 degree. And so if the polarizing angle is 56 degree, what does it mean? It means when an electromagnetic wave which is unpolarized is incident on a glass surface at an angle of incidence of 56 degree, then actually the reflected wave will be plane polarized, having polarization vector perpendicular to the plane of incidence. And so in this case, you can see what will be actually the angle theta r. So you can see this theta r will be equal to 90 minus 56, and this will be equal to 34 degree. This is a proper example. So for air and glass pair, the polarizing angle or Brewster's angle is 56 degree. So you can see that Maxwell's equation predict an effect which is long known in optics. In fact, this Brewster's law is extensively studied in optics, and we can explain this Brewster's law on the basis of Maxwell's electromagnetic theory. Now let us consider another example, which is in fact a most important example. You can see these two figures. In fact, in this figure number A, you can see I have shown that a plane polarized electromagnetic wave is incident on the surface of water. See this figure. And I have shown this plane polarized wave by this sign of arrow, and you know the sign of arrow actually represents a plane polarized wave, in case of which the polarization vector is in the plane of incidence. So we have considered that the incident beam is a plane polarized beam and its polarization vector is in the plane of incidence. In fact, in this case, if it is incident on the surface of water, then actually there will be no reflected wave. It means reflected wave does not exist, because you know the reflected wave has the polarization vector perpendicular to the plane of incidence, and the incident beam actually does not contain such a polarization vector. And so in this condition, there will be no reflected wave. Only transmitted or refracted wave will exist. And this transmitted or refracted wave has also polarization vector in the plane of incidence. And in this case, you can see that the angle of polarization or Brewster's angle will be actually 84 degree. You can calculate it here, that here in this case you can see the first medium is air, and so N1 is equal to 1. And the second medium is water, and for this N2 is equal to 9. In fact, in case of pure water which is non-magnetic, refractive index will be actually equal to 9. How? You can see it from here. You know, for pure water, the dielectric constant epsilon r is equal to 81, and this is relative permittivity or dielectric constant, and you know that n is equal to root over epsilon r for a non-magnetic medium. So in this case you can see that this will be a square root of 81 and that will be equal to 9. So in general you take that refractive index of water is 4 over 3 or 1.33, but in case of pure water, since the dielectric constant is 81 and it is a non-magnetic material, so in this case the refractive index of this pure water is not 1.33 but it is equal to 9. And so in this case, if we want to calculate the polarizing angle theta p, what will be this? You can see this theta p will be equal to tan inverse n2 by n1, and since n2 is equal to 9 and n1 is 1, so this is simply tan inverse 9 and this is equal to in fact 84 degree. So angle of polarization in this case is 84. The remarkable fact is what? As I have told you, if a plane polarized electromagnetic wave, particularly let us consider the radio frequency wave in which the polarization vector is actually in the plane of incidence, will be incident on this water surface, then the refracted wave will be also plane polarized with the polarization vector in the plane of incidence, and there will be no reflected wave present in this case. So you can see this water does not affect this wave, because in case of incident wave the polarization vector is in the plane of incidence, and in the refracted wave this is also in the plane of the incidence. So the effect of water on this incident wave is nothing. It is not, this wave is not affected by the medium water. And similarly, if we consider that our incident beam is plane polarized, but if the polarization vector is perpendicular to the plane of incidence, see this figure B, here we have considered that actually the incident beam is also plane polarized, but in this case we have taken by this dot symbol that the polarization vector is perpendicular to the plane of incidence. In fact, in this case the reflected beam will exist, and this beam will have polarization vector perpendicular to the plane of incidence as it is in incident beam. But in this case there will be no transmission, no refracted beam will exist. So here we can also see that this water does not affect the incident beam, because the state of polarization is not affected by this medium water which has refractive index equal to 9. So actually this is an extreme case that in first situation we have considered the unpolarized wave, and you have seen that in case of unpolarized wave actually the reflected beam is plane polarized having electric field vector or the polarization vector perpendicular to the plane of incidence, and refracted wave has polarization vector in the plane of incidence. So in this case this unpolarized beam is split into two plane polarized beams of opposite polarization. But in case of plane polarized beam these two events takes place. But in general, if we consider that our wave is neither purely unpolarized or purely plane polarized, then what will happen? Let us now examine it. So we can see, even if the unpolarized wave is reflected at angles other than the Brewster's angle, we have actually considered the angle of incidence equal to Brewster's angle in previous examples. But if in general we consider that the unpolarized wave is reflected at angles other than the Brewster's angle, then actually there is a tendency for the reflected wave to be predominantly polarized perpendicular to the plane of incidence. In fact, the success of dark glasses which selectively transmits only one direction of polarization depends on this fact. In such a case, the degree of polarization is defined in a particular manner, that how much there will be a polarization, that is determined in terms of degree of polarization, and we will see that this degree of polarization is defined in terms of the reflection coefficient in case of the electric field vector perpendicular to the plane of incidence and electric field vector parallel to the plane of incidence. So let us consider this situation, that if theta I is not equal to theta p, then reflected wave is partially plane polarized. How much it will be polarized, that is determined in terms of degree of polarization. In this condition, we define degree of polarization. How we define this? If we denote this degree of polarization by P, then it is defined as R perpendicular minus R parallel over R perpendicular plus R parallel. And you can see actually this degree of polarization will be definitely less than 1, because you can see the number in numerator, which is R perpendicular minus R parallel, is smaller than the number in denominator, which is R perpendicular plus R parallel. And you have already seen what is the actually value of this R perpendicular and R parallel. Actually these are reflection coefficient for perpendicular and parallel components of the reflected light, and by the use of Fresnel equation we have already found the values of these reflection coefficient in previous lecture. So here you know this R perpendicular is equal to sine square theta I minus theta R over sine square theta I plus theta R. And you have also seen that this R perpendicular is what? This is tan square theta I minus theta R over tan square theta I plus theta R. And so in this way we define the degree of polarization. So you can conclude that when an unpolarized electromagnetic wave is incident on a boundary at an angle which is equal to Brewster's angle, then actually the reflected wave will be plane polarized, having polarization vector perpendicular to the plane of incidence, and the refracted wave will be also plane polarized, but in this case polarization vector is in the plane of incidence. But if the angle of incidence is not equal to polarization angle, then actually there will be the partially polarized reflected wave and the refracted wave. How much these waves are polarized, we actually how much the reflected wave is polarized, it is found in terms of this degree of polarization. And you can see this definition of the degree of polarization, and it is defined as r perpendicular minus r parallel over r perpendicular plus r parallel. So the reflected wave in this condition, when theta I is not equal to theta p, is not completely plane polarized, but you can say it is partially plane polarized. So this is the idea of Brewster's law and degree of polarization. We will actually discuss a very important concept in the next lecture, which is actually the idea of total internal reflection, and we will discuss